Yeah. I was thinking, did I set the focal length already? I think I did. Yeah. Is this thing working? Just there's so much background noise in here sometimes. It's like, I feel like that fan wasn't running last time we were in here. Am I wrong? Maybe it was. I don't know. Anyway, I'll begin. Dear Father, we thank you for this day. I thank you again for this class, this time we have to study your creation. Just help us to glorify you, what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So today, I'm going to talk to you about linear transformations and their matrices. All right? So, first order of business. First order of business is to deal with the most important and sort of basic theorem, right? Which is theorem if L is a mapping from, let's say, Fn to Fm, then there exists a unique A in Fm by n for which L of x is equal to Ax, right? Moreover, we denote bracket L equals to A in this context, right, is the so-called standard matrix of L, right? Now, I don't mean to say that the notation A is reserved, certainly not. But if we take the mapping and put it in brackets, then that's the standard matrix. All right. And I guess I'm kind of there is a criteria that needs to be stated for L. What is it?
Linear.
Yeah, linear. Linear transformation. Or I'll just say linear map because it's less writing. That better be the case, right? Okay, so here it is. The proof is really just a calculation. We have for x, well, we can write x as the sum, right, over x sub I, e sub I, right? But that's the standard basis. Any column vector can be expressed as such, and then L of x is going to be equal to, my bad, let me, L of x equals to L of the sum of xi, ei, like that, right? But, of course, we can, by linearity, pull out the sum, right? And that is exactly the matrix column product of a particular thing, right? This is a linear combination of these vectors. You can rewrite that as, this matrix, L of E1, L of E2, L of, how many E's are there? Oh, n of them, right? L of En times the x vector. And that's just literally like, if you think about it, let me write it out a little bit. Let me write it this way instead. Yeah. so you can kind of visualize it more directly, right? So when we take the dot product of this, right, with that, what do we get? We get x1L of E1, x2L of E2, so forth. So it's exactly that, right? But of course, that's just x. And so this, apparently, is the standard matrix of L. So to calculate the standard matrix, we can just take, what is the linear transformation due to the first, second, third, all the way out to nth standard basis inputs, and those will form the column of the standard matrix of the linear transformation. All right, so if we call this equal to A, then Aij is equal to what specifically here? Excuse me. So J is the column index, right? So if we're in the jth column, we're looking at L of Ej. And we're looking at what? The ith component of that, right? That's the formula for the matrix. So far, so good? All right. Theorem. If L1 and L2 have composite L1 composed with L2, then the matrix of L1 composed with L2 is equal to the matrix of L1 times the matrix of L2. And again, I'm presupposing here, of course, that L1 and L2 are, linear transformations on appropriately sized column vectors, yeah? And so let's prove this theorem, yeah? The way it goes is pretty simple, if I remember right, because we can just look at, let's look at the matrix of L1 composed with L2, and let's look at column J of that. All right. I'll run my proof through a column notation. Let's look at the jth column of that matrix. What would it be by definition? So my definition of standard matrix for the purpose of this lecture was that it's the matrix formed by concatenating the values of the transformation at the standard basis as columns, right? So in particular, this would be L1 composed with L2, right, of Ej. All right. Now, I may get hung up at this level of notation. If I get hung up, then I'll drop back to like the index stuff, We'll see. Then, okay, well that is what? Well, that is L1 of L2 of Ej. But by the previous theorem, that's what? That's the matrix of L1 times, right, L2 Ej. Now L2 Ej is playing the role x did in the theorem. It's a vector, right? Then what? I mean, again, this is the standard matrix of L2 times Ej. But by our basic matrix math, if we take a matrix and multiply by the jth standard basis, what is that? What does multiplying a matrix by the standard basis give you? if I have 1, 2, 3, 4, 5, 6, and I multiply by 0, 1, 0, what happens? 2, right? 5, so what is that? Second column, right? So multiplying by the standard basis selects that column, corresponding column. That is the jth column, column J, of the product of L1 and L2. But, see, if you want to show two matrices are equal, there are various approaches you can take. You could show that, well, here would be a horrible way to do it. You could show all possible submatrices are equal. Ugh. You could show every column matches, column-wise it matches. You could show every row of the two objects match, right? Or you could show that every component-wise equality implies matrix equality. But here we've shown that the jth column of that is the jth column of that. So it then follows that the matrix of the composite is equal to the product of the matrices, like that. Now, a good undergraduate linear algebra book will make the case that matrix multiplication is defined as it is for this to happen. Like, we define matrix multiplication as we do precisely because we want the matrix of the composite of two linear transformation to be the product of the matrices of the transformations which have been composed. You can also make the case for matrix multiplication being defined as it is by studying solving systems of equations by a substitution. If you substitute a system, like a linear substitution into a system of equations, and then like you study the equations which define, if you study the matrix which defines the linear substitution, and the matrix which defined the system in the original set of variables, what you'll find is that the coefficient matrix of the substituted system is exactly the product of the matrices of the given system as well as the substitution matrix. So like that's another way you could motivate the definition of matrix multiplication. But however, anyway, it is defined and there it is. Any questions? Okay, so there are other less tricky things, right? Like you know, the matrix of L1 plus L2 is the matrix of L1 plus the matrix of L2. That's super easy to prove, you know. And if you've got a constant here, you can pull it out, right? So these things are true. And this is actually, my first theorem is actually if and only if, by the way. A function, right? A function from Fm to Fn, a function from Fn to Fm is linear if and only if its formula can be written as a matrix multiplication. All right. So they're one and the same. All right. Now, also notation I should mention, lest I forget. L sub a of x equals to ax for all x. In other words, the matrix of LA is equal to A. So this L sub A, I use this notation for the linear transformation defined by left multiplication of the matrix A. All right, so yeah. Okay, let's see, anything else I want to tell you here? I think that's pretty much it for this. All right, so let's move on to see, I could look at coordinate change here, but I think it's healthier to look at coordinate change for the abstract vector space and then specialize to this case. So, all right, that's my approach, is to try to set up the discussion of coordinate change in the abstract vector space context, and then we'll apply it back here. All right. So Now that we talked about linear transformations of concrete linear transformations, I sometimes call these linear transformations of column vectors. Well, now let's talk about a linear transformation, a linear map from one finite dimensional vector space to another. All right? So let's let V and W be vector spaces. All right? And I'll stay over the field F, although, I mean, honestly, pretty much in this course, we're almost always using reals. But I do like some complex examples thought of as real vector spaces. Like that, to me, is an interesting place to play with. But so here we go. Vector space V to vector space W, linear map. And let's fix our notation. Let's let V equal to the span of beta, and W equals to the span of gamma. All right, where we'll use the notation beta is equal to V1, little v1, v2, dot, 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 vn, and gamma will be, let's say, w1, w2, dot, 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 wm. All right, so I'm keeping with my use of n, and n for the domain dimension and m for the codomain dimension. All right. In this case, so let x be an element of V, then x is equal to a sum of, well, x sub I, v sub I equals 1 to n, and you might recall that the coordinate vector of x here would be equal to x1, x2, da 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 da, xn, because those are the coefficients which are needed to express x as a linear combination of the basis v1 through vn. Now, I get tired of this notation, so I'm like, why have one notation when we could have two notations, right? So I will also use this notation as it's helpful for me. So this means the x vector, the coordinate vector of x in the beta basis. All right, here x is an abstract vector. X could be a polynomial, x could be a matrix itself, like a 2 by 3, whatever. But when I put the brackets around it, puts a beta, that's a column vector. It's an element of Fn. Okay, now consider t of x is equal to what? Well, t is an abstract linear transformation, right? So we can write that as, and I'm going to pull the sum out just to start with, just to, if you don't mind. I hope I won't lose you doing this. I don't think I'm going to. I equals 1 to n of xi t of vi, right? So I use the linearity. I use the linearity of t to pull the summation out, pull the scalar multiples out. Now, I'm going to use the fact that gamma is a spanning set. I'm going to use that to let's see here. Oh. Yeah, there's something else I'm always nervous to say here. I'm not going to say it because I don't. my student in Texas is telling me he has an office now. It's probably a better office than mine. It's probably got walls. Anyway, no, he's probably in an office with like 3 or 4 other grad students in all likelihood. I shared a space with like 6 people at one point and 20 people at another. It's just like, yeah. Anyway, I digress. So the t of vi we can express as a linear combination of the w's, right? So we can write this as, like a sum I equals 1 to n, xi sum, let's say j equals 1 to m of, all right, fine. I guess if I'm going to accept, here's what I have to do. It is t of vi, right? I want this. I want to measure this with respect to the. I'm expanding it with respect to the gamma basis. So I need to look at the gamma coordinate vector of that. All right. And then, what am I looking for? I'm looking for the jth component. All right. That is the coefficient of wj needed to form the span here. So I can write this as like the sum I equals 1 to n, the sum j equals 1 to m of the matrix. Well, let me well, let me just call this thing, for the sake of just discussion here, a ij, right, x sub I, w sub j. Here, a sub ij is equal to the jth component of the coordinate vector of t of vi gamma sub j. I've just introduced a letter to make it kind of more obvious what's going on here. So that A is obviously a matrix, and that is, what are we looking at here? I mean, that's like a, of course I can put the j out here instead, right? I can put the j first. I can switch the order of the sums maybe to better emphasize what's going on here. So if you look at this piece right here, right? This is the jth component. Let's see here. So what you're actually looking at is like the not that I've written. It's not that I've written anything wrong at the moment, Ernesto. It's just like I know there's a slightly easier notation to like communicate what's going on here. It'll come to me. Let me just write more. Usually, as I write more, I'll figure it out. But this is a matrix column product, right? It's the basically this is like matrix A times well, I can't say just x, right? It's not x. It's the coordinate vector of x, right? It's the coordinate vector of x with respect to the beta basis, right? And it's the jth component of all that. I think. Okay, so what happens if you take this equation, right? And you look at, like, I think I know what the, I know. I have, like, I don't know, at least 3 or 4 pet potential definitions for the matrix of an abstract linear transformation, all right? And so there's like different ways to come at it. And I think this becomes easier to put together as a whole if instead of looking at tx, we look at the coordinate vector of tx. So if we look at tx, t of x, and we look at the coordinate vector of that, what would that be? I mean, we use, it's in W, right? So we should look at the gamma coordinate vector of this, right? And by the calculation I just did, right, you get, because remember the coordinate map is an isomorphism, so it's linear, we can pull the summations out of that and everything, right? So we get some like I equals 1 to n of x sub I, and then that matrix I had over there, right, T of vi sub gamma, the jth component of that, and then you got the wj, right? So we got the wj gamma here. So all I'm doing is basically what I'm doing here, Ernesto, to track is I'm going back to the calculation I just did on the other board. All right, and what I'm doing is I'm hitting this equation. All I'm doing is I'm taking the gamma coordinate of this is equal to the gamma coordinate of that. All of this is just numbers. That's the abstract vector. So all of this sums and scalar multiples pull out of the coordinate mapping. It just leaves you with the coordinate mapping of that. What is the coordinate mapping? Where does the gamma coordinate map send wj to, though? What is that actually? Remember? Where does the coordinate map send the standard basis to? I mean, excuse me, where does the coordinate map send its own basis to, right? By definition, it sends it to the standard basis. So this is exactly like EJ in the as an element of, whatever FM, I guess it was, yeah, because W is m dimensional. Okay. Right? So then what? So if you look at this, then we have all right. Okay. I'm gonna get it. Sum over I. Oh man. X sub I. And there was a sum over j I lost here, right? should be written somewhere in here, maybe here. And then we have, sum over j, 1 to m, of the t of vi of gamma of j times ej. All right. Let me write this. I'm sorry. There's some stupid ingredient I'm missing at the moment to see clearly through this stuff, and it's driving me nuts because I know this can be done in about like 5 minutes if it's done clearly. All right. This has got to be understood as like a matrix multiplication of some sort or another. So let's see here. All right, so we've got the sum I equals 1 to n of x sub I, and then let me just, so what we're looking at here is like t of vi of gamma E1 plus t of vi of gamma E2 t of vi of gamma E, how many? EM. If I'm not careful, I'll cycle back to where I started. That'd be funny. I get done with this. I work my way back to tx of gamma again. Like that could totally happen at the moment. All right, so let me see if I can write this down. I've got something like a matrix T of V1 oh, goodness gracious, what is wrong with me today? All right, I'm going to stop the camera here for a second, get some coffee, and fix it.